I will start the presentation. My name is József Szalai. I'm the leader of the Consteel Solutions company, and my colleague Bálint will continue after my presentation with one of the key engineering developments, the members with double C sections, more in detail. A few words about the schedule. We have some small improvement in the installation process. Then I will show you the brand new project center. We have a new navigation overview function. A couple of new things in the project center like tutorials, example models, parametric models. I will show these. We have some Descript novelties and some novelties in Steelspace, in model viewer and commenting options. We have a brand new Consteel manual. I would like to present it. And we have a new handling way of cross sections in Consteel. This is my section library. And we have a large development in the import processes. All of these are centered into the import center with a completely new model import workflow. We have a new support type. This is a compression only support. And at the end of the presentation, my colleague, as I said, will show a new structural member with double C section. And you may know that we have also a brand new module called Falcon. This is a wind generation module, wind load generation module based on CFD simulation. And this is a quite huge development spanning with almost 3 years of developments. This is the first results. It is now in beta phase. And so we will have tomorrow a separate webinar on the functionality of this module. Please register to this webinar as well if you are interested in that. Okay, now I start with the installation. Now we have two options for installing Consteel: install for all users or install for me only. And this is because in the old installation process, the user needed a system administrator right in the computer because it installed into the program files folder. Now it is not necessary if the company has some kind of protocol that the user has no administrator right, system administrator right in the computer. They can use this first option, and with this installation, the Consteel is installed into a local folder only accessible for the local user, and that's why the system administration right is not needed. So it is a beneficial tool for those who up to now always ask the system administrator to allow or install the Consteel into the to the computer. Okay, I start now the software. We have our new splash screen. We can see now the new awarded models in steel iron competition. I encourage from here everybody to participate in this competition next year. Soon we will open the submission form, and it is a very good feedback for us if we can receive lots of beautiful models from our users. So this is now the new project center. We have a couple of developments and improvements in this area. This is really the center of handling and managing with the models and knowledge in around Consteel. This is the new home screen. This is a personalized home screen. Here we can see our recent files. You can view in this order with small icons here or with the big icons. Now, not only the saved model, but the opened models are also appearing here. So it is a great tool to select your project you would like to work with. And then you can see how to create new model. You can create by a new empty model, but there are two more options. You can start with just importing a model, your new model, or you can start with the parametric models. Here we have also the news, and here you can access the notifications, which are just announcing the events, for example, the applying for Steel Lion or trainings, what we have next year, a couple of new trainings, and some of the notifications, the most important, are here. And you can go and apply to events. Then this is the home screen. You have the create new screen with the same possibilities, empty model, import model, or here are some personalized models from our parametric model library. In the open, you have the open from computer or open from cloud and the recent model again. And we have a brand new learn area where you can have a couple of new example models and learning materials all loaded into this project center. And you can filter these contents, filter by design problems, structure types, or building types. So if you are looking for tapered or hinge members, these are the example models with these members, and these are the connected learning materials. Or you would like to see the fire design, you can access directly this knowledge base material from here, and you can access directly the connected example model for this fire design material. So this is a good way of supplementing your knowledge and supplementing the Consteel manual with these contents here. And we have a brand new type of learning material. This is the tutorial type example model. So these are tutorials. We have now only two, but we will increase the number of different tutorials on Consteel functionalities. I would like to start with one of them. This is basically for new members in Consteel, but we will implement several function into the tutorial, which may be help for existing users as well. I just would like to open and show you the functionalities of these tutorials in Consteel. So I start with this new model. First of all, here we have a brand new navigation overview screen. And now Consteel starts with that screen. You can check it out that you don't want to see it again. If you are checked all the possibilities, these are helping the engineer to look at the most important model navigation tools in Consteel, how to navigate, how to select different selection types here with a small GIF and animation, how you can do different selection, different types of model views, background color, and how you can access the different help material. So you can see these tools, and you can even now have the possibility to change your preferred way of navigation, how to move, rotate, and zoom in the model. You can This is the Consteel type of navigations, but you can now select other software. Like if you like Revit, then these are the Revit navigation types, and you can select Revit if you are familiar with this and you want to change this. Okay, now I stick to the Consteel navigation set and push the OK, and now you can see that you may find this in this help menu. Okay, so after that, the tutorial model is starting. So this is a tool in Consteel when inside the model we can communicate with the user and lead the user how to use some Consteel functionality. This is a very basic model in which we would like to go through on how to do a lateral torsional buckling analysis and design in Consteel in a very simple model, but showing some of the unique features of Consteel. So it is a step-by-step journey. Now I go to the next stage, a small description about the model. The next step, we automatically jump into the analysis results. We can see here the results, some text about what we are seeing now, how organized, how the analysis results tab is organized. Then we go to the next stage, which is specific in Consteel, the buckling analysis, and you can see this functionality that we can lead what to see, lead the user what to look at in Consteel now. The elastic critical load factor, it is explained here. What does it mean? How it is calculated in Consteel? Why it is important? Okay, then next, it asks the user what to do, asks to perform the global checks. So we push the button, and now we have all the checks according to the design standards, and we can see here the lateral torsional buckling utilization and some explanation. So we go back to the model. Now it asks to select the load because we have to, according to the text, we have to change the position of the load. So we go to here, select this position, OK, and go to the next stage. We have to start again the analysis. It is explained what will happen. So we will have a different elastic critical load factor. It is explained, and even a knowledge base material is linked here, which can be accessed, which explains what's happening more in detail. And then in the next and final step, we have to perform again the design, and we can see that we have even the same bending moment diagram, but because of the different lateral torsional buckling critical factor, we have a much higher utilization now, and it is automatically handled in Consteel. So I just want to go through in this new tutorial tool what we developed into Consteel to communicate inside a model and lead the user throughout a whole process of doing some function in Consteel or working with some function or even with a model in Consteel. Okay, so I now go back to the project center. And I would like to next show you the parametric models. This is also a novelty in Consteel. So I push this option and I create a new model in which I want to start with a predefined parametric model chosen from the model library. So this is now the parametric model library. We can even filter these libraries, what we would like to select, frames or trusses, what types of building, halls or hangars, and there are a little description about on the model. We would like to increase the number of different types of parametric model to start with in a Consteel. Now I choose this one and start to create, and it leads us on creating the parameters now with 3D hole. We have to define the geometric parameters here. It is very important that it is built on our Descript functionality, but now it is directly accessible, creating a new model from the project center. And you can see this is a Descript new development, that now the Descript screens are completely renewed. We have now this good looking screens, good looking dialogues, and we have a couple of new possibilities, more validated and my stable dialogues can be created in Descript. And these are used directly in the project center to access parametric models. So I accept these parameters. Now it creates the main frames of the whole. The next stage is the purlins. I have to define the purlins here. I accept these. The purlins are taken to the top of the beams with the necessary connection element, with the necessary connection types in the connection element. And the next stage is the wall purlins, and when it is accepted and done, and we have a final message that the parametric model has been created successfully. Okay, and this is one of our parametric models from the library. It is a complete model with load transfer surfaces. All the members are connected in the right way, so you can now use it as a starting model for your hose. Even some model portions are created. Now on this model, I would like to show you the novelties in Steelspace. So I uploaded this model in Steelspace, and we have a couple of new functionality in Steelspace which can help your collaborative work in that cloud-based tool. So first of all, we developed some new visualization tool in the model handling. You can now see the hunches and tapered members in Steelspace with the necessary parameters, and the model portions are now received here, and you can select portion view here. Like I would like to see only the main frames, the primary bearing system. You have a couple of viewing options, like just seeing only the model portion, or this type of view where the other portions are in a shaded view, etc. And you can select any other. This is the bracing, the purlins, wall purlins, etc. So this is a new viewing option that all the purlins can be visualized in Steelspace. The other improvement and development in Steelspace is the new commenting tool. We have introduced multi-level commenting. You can do a global comment. You can make a global comment, object-specific comment, or object group-specific. The global comment means that it is valid for the whole model. So we have here the whole model, and here in the bottom I can push this and do a comment here. And now it appears here in the commenting region, and all the invited collaborators are can look at this comment, can reply to this comment, and this is the global comment. If I would like to take a comment on more objects, like I select, for example, all these rafters, for example, and in a specific view, now I do the commenting. Now it appears here. As an object specific comment. And if I would like to just and an object group specific comment, and if I just would like to make a comment to just one member, for example, to this column here, I select this column and make the comment here, column. Okay. And all the people with whom I share the model can see these comments. If I select the global comment, I can see this. If I select object specific, then I click to this comment, and the original view is created, and I can see as a selection the object for which the comment is here. And if I select the object group specific comment, it is somewhere here. And now I can see all these, all the selected objects, object group for which this comment is valid. And for all comments, you can delete, you can answer, and you can have collaboration with your colleagues. So these are the new developments in Steelspace. Okay, the next topic which I would like to show you is our brand new Consteel manual. You can access from the same menu from Service Center, the online manual, but now it is in a completely different place, opening in a new tab, in a new with a brand new look. This is the new Consteel documentation center. Everything is taken to here. From now on, you can have the Consteel manual. You can see the Consteel manual, the Descript manual, the new plugin documentation area. Now we have two plugins, converters, and the new Falcon plugin already uploaded here. The Falcon manual and the release notes can be seen here. There is a new versioning system, so you can access the older versions, the manual for the older versions as well, if you need for some reason. Now we have the newest one, version 18. There is a language selection, but now it is only available in English and Hungarian. You can select what should be in light mode or dark mode, the background, and you have a very good search option in which it is saved the recent searches. You can do some favorite searches from your search, and if you start to to type something, you can see the detailed info where this word is found in the document, and you can just go very quickly to that. The document is in a very brand new looking. You can see the structural modeling, for example, in these cards. You can see the main sections, main chapters, and you can very easily and comfortably navigate throughout what you would like to see in this new manual. Okay, the next thing which I would like to show you is the new cross-section handling. I go back to this model and go to Structure Members tab and open the section administration. We have now some new buttons here, My Library and Save to My Library. First, I would like to show you the My Library. This is a new area for your cross sections. You can load cross sections and save to this library. This library is saved to your local computer and can be accessed from any other model. So it is a central place for your favorite cross section, organized in a way where you want. You can create new folders, and in folders you can have your loaded sections. Like it is a valid section. Here are some info about your sections. You can go back. You saved some favorite AGA sections, for example, or favorite IP sections. And you can put here even user-defined section, like this is a user-defined section, what you want to access from all of your models. So if you have a specific library, for example, from cold form, user-defined sections, this is a user-defined Sigma type sections. So this is not a parametric, but I defined it manually, and I can save it to my library, and then it is accessible from all of my models. And I can select one or more sections. Even I can select a folder as well, and I can load these sections. If there are some conflict between the names, I guess there are conflict, for example, between the names of IP sections, then it is automatically identified and loaded here. Here you can, here we have the sections already in the model and the loaded sections. And now I have everything here, what I loaded, even my user-defined Sigma sections. And I don't have to define all the model again, this type of section. And how to do this? I can select any sections, like I select now this, for example, this Zeta or cold form Z profile section, and save to my library. I go to here. I can even create a new folder for this, like Z sections. Create, go to here, and save to this. And then if I go back to my library, from all the models, now I have saved this Z section for this into this this folder. So it is a good way to create my own section library where I just with one click, I would like to load into the software when I start a project, and usually I like to use these type of sections. Okay. So the next new functionality is the import functionalities. I go again to the project center and select create new. From the create new option, I select the import model option. Now it opens a new Consteel. Okay. And opens the brand new import center. So this is a centric field where we can handle all the models compatible with Consteel, and that's why we have to first select a folder where I have my models. I select this folder and the Consteel loads all the compatible models what can be imported into Consteel. Now these models are IFC models, IFC 2, 3 and IFC 4 type models, SAF models and smadsteel models, which are our own, which is our own model type. Smadsteel models exported from Axis. So the Axis export functionality creates a smadsteel model, and also it can come from Grasshopper as well. If we export from Grasshopper using our Pangolin tool, then it will be also a smadsteel model. So we have now here all the different model types: IFC models, SAF models, which is an XLS type model, and the smadsteel models from now from Axis. There is here a preview functionality. Preview is available for IFC and smadsteel models, not available for the XLS models from SAF. So you can see the selected model as a preview. Now it is, for example, a smadsteel model. It is a preview about this model in our using our Steelspace engine, and I can select an IFC model as well, for example this one, and view the IFC model. Now it is a more detailed model with some connection elements as well here, and this will be the model which I would like to import now. So this is a preview function in which you can just previously see what is really the model, what you want to import. And this is a complete IFC viewer, so if you have a more complete model with all the connection details like the bolts, then you can see all of these as well. So you can see here that here you have all the plates and walls and everything in this model. Okay, so now I select this model. This we created to show the whole import process what we developed for this new version. So it is a step-by-step process. First, we loaded now this folder, choose the file, the compatible model type, and go to the next step. Now a model conversion is done. The model conversion converts all the models into a smadsteel format, and it is completely renewed in this new version. In IFC especially, we developed a lot of features in this conversion. The supported objects are the IFC beam, column, member, and plates objects. We can handle B-rep representation and extruded representation. We can handle original or cut length. And we have a section conversion, which is somehow the heart of this model conversion. This is a very problematic field usually, And we have a multi-level section conversion where we try to match the sections in 3 levels. I will show it later when I open this model. So here we also have a preview mode. So we can preview the model, but now in the Consteel modeling space. So now it opens the model, but it is now not creating real members. Just we can see how it will look in the Consteel model space. And if I want to change the position of the model, I have the possibility to set the coordinates, or I push the change button, and then I see here the bounding box of the whole model. And for example, I would like to set here the model. Then I push the set, and now in the new preview view, I can see that this model will be somewhere here. Okay, and if I'm ready with the positioning, then I can push the import button, and now the import, we can see here, creates all the necessary cross sections, members, plates, everything, and imports the model here. Okay, so this is the imported model. What we can see now that a couple of elements are imported. For example, all the members. These are the beam or column members in the IFC file. And I would like to talk a little bit about the cross-section conversion. We have 3 types of cross-section conversion. The first one is a match by name. So we try to matching the names. For example, here the name is AGA 140. Sometimes it is spelled differently in different software and go to the IFC file in a different format. But we have a conversion file to handle this issue, and we try to match with the Consteel names. So this is the matched cross sections. If we don't find direct match from the conversion file, there comes the second level is matching by parametric section type. So if it is a parametric section type, like it is a rolled section or a code form SEJ section, this one, it is signified. This is the name, and in parentheses there is an IFC. That means then in IFC, this is the name of that section. We haven't found suitable Consteel with this Consteel section with this name, so we converted this, but we have found that this is a parametric section in the IFC model with the parameters, with the this 85 as the height of this section and 5 millimeters as the thickness of this section. So this is an SEJS section, a cold form. We have in Consteel the same parametric section type, macro section type, and we match this and matching the parameter values as well. So this is the second level. And if we haven't found all of this, for example, this is, I just would like to show, this is also a parametric matching, and this is reinforced concrete section where we can receive the basic data from what is the geometry of this concrete section, and it is created in Consteel and taken to here. And if we haven't have any matching like this, then we put a placeholder. So this is this big section is a placeholder just to show you that this section we haven't found any matches, not in the name conversion file and nor as a parametric section type. So you see here that this is the name in the IFC file of this section, and you have to change this section if you want to use it. Okay, so these are the section conversion. Now I would like to talk a little bit about the member conversions. Basically in IFC, there is two types of member representation. And this is the boundary representation, or BREP, and the other is the extruded. The boundary representation cannot be used for real structural elements, so we cannot turn these objects into structural members. We just, for example, take this frame as a boundary representation in IFC. These are just two-dimensional figures in a separate layers. So these are not real members, but showing that these are planes at the boundary of the cross-section and the member, and all these planes are different two-dimensional figures in Consteel. So now we are receiving these members as well in this representation, but this cannot be used as Consteel structural member because we do not know anything about the material, the cross-section, etc. We have the shape here, but it is just a geometry and not a real shape. The other representation type, object or beam member representation, is the extruded area, and all the others are that type. So in this type of export, IFC export, we have the reference line, like in Consteel here, or the reference lines, and on the reference line we have the cross-section for which we can use the cross-section conversion, and that creates a complete structural member in Consteel. We see a couple of other other objects here, and these are the plates. Plates here, and these plates are part of the IFC model as the part of the connections. So it's not necessarily needed in Consteel, but we can include these plates as well. You can just choose all the plates and then delete these plates if you want, but we can even include the plates, all the plates in a Consteel in the right geometry, with the right geometry and with the right position. Now, it is very important to see, because when a detailer makes a model, lots of plates, for example, connection as the structural objects inside the connection are modeled as beams or members, because it is much easier or comfortable to handle. And then these beams are also imported in Consteel with the parametric cross-section. So it is very important to see that these beams are part of the connection, because rather these beams are plates, but just modeled as beam objects. Okay, but these are plates and part of these imported IFC models. Also important to see that there can be two options to import extruded IFC beams or members into Consteel, keeping the original length. And now this is the option. We kept the original length. That means that if I choose this one, it goes from the point to point. Sometimes it goes even further than the theoretical node of the connection. And because of that, of course, it is overlapping with the connection elements here, which are obviously not needed now in Consteel, but this is the member with the original length, and there will be an option in Consteel when I want to import the model with the cut length, when the connection macro in the detailer software in Tekla, for example, makes operations, geometric operations on the members and cut the ends, for example, here at the end of this end plate, and we can receive the member with these cut length as well. But we think that maybe this type of import is better because we can have more possibility to make suitable model for structural analysis. And there are problems, of course, in the connectivities, because now this frame here and these members are not connected in the detailer model. You can see here, and it is also a very important novelty in Consteel that now we don't import the members with the original reference line, because the reference line created in the detailer software usually do not have any structural meaning, while in Consteel the reference line has a strong structural meaning for the analysis and design, and that's why we convert all the members and import with the reference line taken to the centroid of the cross section. So that's why every line is now in the centroid. The member itself is in the right position, as you can see from this view, but these centroids are now for this frame and for these two members are not connected, and we should connect if we would like to go further and calculate it in the right way. Okay, so this is about the import of models. We would like to present a protocol for different detailer software like Tekla or Revit, how to export from this software in the right way the IFC model in order to have the most possibility in Consteel during the import process. Okay, and next I would like to show you go back to the project center and open a new model with this compression only support and show you this new functionality. So I open a very simple model and would like to show you what does it mean in Consteel, this new support type with compression only, a degree of freedom. I created a simple beam model with simple supports and with some cantilever here and a simple load here. And this is a fixed but pinned support. Here are the degrees of freedom, and these are also pinned supports and fixed in all the directions. So if I run quickly a first order analysis, I have two types of loads. Gravity type load towards minus Z direction, and this is an upward load towards positive Z direction. And in these two combination, I have these two types of deformation, down and up, and we have different reactions here in the supports. So if I have a downward load, here we have a compression in the support. Here we have tension in the support and again compression. And this new types of support, which I would like to show, it is an option. For example, if I select this support and change it, this is the original support, and we have now a new tool here, a compression only support definition in the Z direction. What does it mean? That it will keep the support if we have compression for gravity loads. So if we have a reaction force in the support from the minus Z loads. So we have a compression reaction force in this Z direction only. So I created this compression only support. In this case, I have to check this compression only support in Z direction. Then the Z row is absolutely overwritten. I cannot change anything here because it will be fixed in that direction, in minus Z direction, and will be released in upper direction. And if I change now this support and run again the analysis, then I can see that now we have a different deformation for this load. It kept these two supports, but this support is released because it got tension, so got a reaction force and released the support. It is a simple iteration, and always try to find the final consistent state of the structure with these types of supports in each different combination. So if I see now the other combination, we can see now that here the analysis kept this support because it is a compression support here in the another analysis type. So we can see here the reaction forces. Here we have a compression in the support, so this support is kept. In the other combination, the support is missing, and we have just these two reaction forces. For if I change it accidentally in other supports, for example, change these supports as well, I would like to show you what's happening. So now these two supports are compression only supports. Then what's happening? In this combination where we have upwards loads, it releases this one and keep this support because it gets compression, these two supports, and it gets tension, so it releases. But for the other combination, we get the message that the first order analysis result displacement higher than the allowed limit. So that is because both of these supports get tension and release both the supports, and then it will be an unstable model. So the other combination, we do not have any results now. So you have to be careful with using these supports because it very easily can make the model unstable. So it is not an incrementation. We wanted to keep the simple application and wanted to keep all the other linear calculation like the buckling calculation. So for doing the buckling calculation, we cannot apply step-by-step load increment analysis for the second order nonlinear analysis. We just have to seek for a consistent state, and going further with this state, we can run all the second order and the dynamic and buckling analysis. It is quite similar as the tension bars are working. And one more thing, using this element, it is always considers the local coordinate system of the support and always acting in the local Z direction. That's why here we can see this tool that compression only support in Z direction. So if we want to apply it, for example, in another direction, not vertically but horizontally. I created another model here. Here we have a vertical column, and here is horizontal supports. Maybe we have a wall here and we have to release this support if it gets tensioned relative to this vertical wall. Then we have to set suitably the local member Z direction, and then take the support, or model the support as a local support to this local member coordinate system, and set the support accordingly. So if I see now the analysis, now everything is a complete support. We can see that in this combination, these are the reaction forces. It gets tension, and if I change this support into compression only in that local Z direction, okay, and run again the analysis, we can see that from the deformation that the support has been released because it gets tension, and now we have a different deformation, and we have reaction forces only here. So this is the compression only support. It is a simple iteration. During the iteration, the software tries to find the consistent state in each different combination and releases the tension supports if necessary. Okay, that was my last topic. I would like to thank you for your attention, and now continue with the new member with double C sections with Balint.
And now, good morning. My name is Balint Vasilievich Semyen, and I will make the last part of today's webinar about the new features of Consteel 18. And I will speak about a new functionality which allows to easily model, analyze, and design double cold form members made of C or C-like sections such as sigma and similar profiles. Double C sections are very commonly used in when someone works with cold form sections, because this is the closest similar section to the most traditional I sections used for steel structures, without any weld or other requirements. The two C sections can be positioned back to back, immediately close to each other, or with a gap, fixed at certain positions with adequate joining devices such as bolts, screws, or rivets, or welds, or anything basically. And this way an I section can be formed, and then this I section can be used the same way as is normally used, most typically for floor beams or for columns carrying mostly compression force, or also for wind load if it's a sidewall or end wall column of an industrial building. And ultimately, you can even make complete structures made of cold form members. WC sections can be used also as a main framing profile for columns, beams, or even for a complete porta frame. Even earlier, since the very beginning, it was possible to define in Consteel such built-up sections by combining several individual members. Each individual member had to have its own reference line, positioned at the right location, eccentrically or without eccentricity. It was always a possibility. And then at the locations where the real structure has physical connections, then the engineer could define link elements or rigid bodies or virtual beam elements. On these virtual beam elements or links or rigid links, any sort of releases could be positioned. So basically, the structure could be modeled very closely to the reality, but it was not very easy. It required quite a lot of work, and especially when a complete structure was about to be built from these profiles, then there were a lot of issues at the connections when such a double profile was connected to another double profile, because even if it is just a double profile, it has two reference lines, and then the engineer had to connect both of these lines adequately into the right location. This is now a Consteel model where you can see on the left side two such old style built-up profiles. They can be very complex, made of several profiles, but if you look to the structural view, now you see that there are individual reference lines, and as I said, these individual reference lines are connected with link elements. And of course, when we are at the end of the member, then somehow we need to make sure to connect the four individual lines to the connecting elements, or try to somehow merge them together into one node which has a beam-like deformation, and then connect this only point to the connecting member. It's always possible, but it's a bit difficult. Now, what we provide in the new version of Consteel is that with just one single reference line, it will be possible to place a double profile, a double C, double sigma, or similar profile. Of course, there are some restrictions. When we use just one reference line, then obviously we will have just one set of consistent deformation. So that assumes that the two profiles will rotate, will move together under any type of arbitrary loading. This can only be guaranteed if the engineer makes sure to provide on the real structure connectors at the right location with the right rigidity. But if this is fulfilled, which is very often anyway assumed by the engineers, maybe sometimes it's not even checked, or hopefully it's checked. But when also with other softwares, such double profiles are used, and basically silently, it is always assumed that the two profiles will move together. Because if that's not the case, then I cannot just merge the two profiles into one. Then the only option remains what we always had in Consteel, to define two independent, or as many as required, independent reference lines and make the connections as required. But if the connectors are placed close enough and rigidly connecting the two members together, then I can combine the two independent lines into just one. I can use just one reference line, and I can use the new functionality. With the help of the new functionality, the modeling becomes much simpler. We have just one reference line, and on the real structure, we have actually two profiles, which can be C sections or sigma sections, or even C-like sections, even a user-drawn section. And we can have even these profiles closely placed to each other, so without any gap, or we can specify a gap. This is possible with the help of a new function, a new macro type, which I will show on this screen. So we already have a certain set of code form profiles available in Consteel, and now we have three new options. The one is for the double C section, where I need to use a section which has a type of C. The second is a double sigma section, where I need to use as input an already defined sigma section. And the third is a double user-defined section, where we assume that the profile which will be used as input is a C-like section, but we are not controlling it. So actually, you can even draw a Z section or any type of section, and you can make a double of it. But what is important, that we cannot guarantee that all the complex deformations will be perfectly, correctly transmitted. At the moment, the functionality works perfectly for the C-like profiles. Okay, so we didn't want to limit. It's up to the engineer to do what they believe. They can always build a a shell model to, for example, try to validate the assumption or go to the first approach to use individual members, connect them with the link elements, and compare the result what this new functionality would provide. It is well possible that it works correctly or adequately well also for sections different than the C, but the function officially works for C sections. So the way we need to define such a double section is that we use as input a single section and we define a gap if that's the case in between. And then like this, we can easily use a double profile exactly the same way as any other profile in Consteel. We can use any sort of boundary conditions on them, eccentric, centric. We can define end releases on any degrees of freedom at both ends. And every functionality in general works the same way for the double section as it works for the usual simple sections. And as a consequence, we will have just one reference line, and on this reference line, we have the double profile positioned. When we go more into details, then it's important to realize that there might be, and there are differences the way we handle this double profile in structural analysis, in the finite element analysis, when we calculate the deformations, and also some differences when we use it for structural design. As I have shown in the finite element model, there will be one reference line with the double profile in it. We have extended our cross-section in our section module to be able to define and to calculate the cross-section properties of double profiles. We use exactly the same meshing technology what we used for the single sections. It's also important that all the section properties are calculated based on a finite element solution of the profiles. We are not using closed formulas. Therefore, any sort of profile what is drawn, and that's the way how it is also supported by the user drawn section. Anything what is drawn can be calculated, and this is not the case anymore for single section, but also for double sections. You can see here a bit strange color. This color means that it's the empty space between the profiles is filled with the filler material. The filler material has zero or almost zero properties, but it keeps the connection between the two elements. This is also one of the reasons why at the moment we cannot offer this functionality for arbitrary type of double sections, because the way how to define this filling area, what is the contour line of the profiles which are supposed to be connected or which are maybe those which are not supposed to be connected it cannot be defined generally. In case of a C-section, the sections always have a vertical wall against each other, so the area to be filled by this filler material is quite clearly definable, and therefore it works fluently for any type of section. So once we are able to define all the properties required for structural analysis to fill the stiffness matrices for the finite element calculation, we can perform exactly the same way the first, second order dynamic calculations, linear buckling analysis, as we did always for single sections. And when we come to design, then we do something different, because even if we said that we assume that the two profiles will move together, on the real structure, it is clear that the connectors are not necessarily positioned continuously along the length. There are gaps between. And if we just remember what Eurocode wants us to consider always the effect of a possible shift of effective cross-section, at those locations when the two sections are not connected to each other, the two sections can displace relatively to each other, and therefore one can assume also that once an effective cross-section is formed, due to the eccentricity of the effective cross-section compared to the gross section, a bending moment can also be formed, and if the displacement is not cancelled by continuous connectors along the length, but just the connectors have a certain spacing. Then between the spacing, the profiles can move a bit. Therefore, this bending, what is caused by the shift of the effective cross-section, in reality can be realized, and therefore this additional bending moment can also appear. So as a certain safety measure and try to stick to the principles of Eurocode, we decided that even if we made the analysis on a combined profile, when we come to structural design, then we convert the internal forces which we obtain on the unified member into two individual members. And for the two individual members, we create effective cross-section models like we always did in the past. So you will not need to be surprised then when we come to structural design. I will show you an example. Then we will see always just a single profile. In Consteel, you will be always along the lengths anywhere you are. You will be always seeing because it has in the analysis model, it has just one reference line, but from design point of view, for each point, two profiles are assigned, and we will be able to see always the results which refer to the left or to the right cross-section. And when I call the section module, I can always decide whether I want to see the left or the right profile. But when I decide to see the left or the right, then I will see always just a single profile. The internal forces are all consistently converted, transformed into the single member. And on this single member, we are calculating the effective cross-sections. And I said, if we have a shift of eccentricity, then we can also take into account these additional bending moments. We have an option implemented in Consteel that if the engineer believes that he doesn't want to deal with this possible consequence of the shifts, then can switch off this functionality, and then we will have a result what is typically given by other softwares. The two eye sections are really considered to move even from this point of view together. I believe it's a bit on the unsafe side, but we decided to give this to the freedom of the engineer. A last word before I show some examples is about what is the validity of this assumption that the two profiles will work together. As I said, if we have just one reference line for the structural analysis, obviously we cannot have two different deformation for the two different profiles. It must be ensured that the connectors are close enough and are rigid enough to ensure that this assumption remains valid. I checked several standards. What do they say about what the required distance is? And it's as usual, there are many different ideas in the different books or standards. This first is from the actual Eurocode. It says that if we have members like on this picture here, there are C-sections shown and they are connected by bolts or welds, then the maximum spacing between the interconnectors is recommended to be 15 times the smallest radius of inertia of the profile, which in this case, it's the minor axis, is the inertia which belongs to the minor axis bending, so 15 times E. That's what the Eurocode requires. The American standard is, as usual, is much more liberal. They only say that they give a general formula where the distance of the connector can be included in order to calculate an equivalent slenderness, and they allow to disregard the effect of the interconnectors if the distance of the interconnectors is less than 40, not 15, but 40 times the smallest radius of inertia. They call it as R. That's the same as the I in the Eurocode, but the limit is much, much bigger. But on the other hand, they say that the connectors must be equivalent to something welded or pretensioned. I don't believe that it's very often pretension bolts are used. This part of this chapter of the American standard is not the one which is related to the cold form section, but this is the most general design standard for any sort of profile. So here, when this sentence was given, probably it was not specifically made for cold form members, but for any sort of arbitrary profiles where pretension bolts are probably more commonly used. In case of code form members, I believe that's not typically the case. So therefore, the 40i is probably a very not adequate and too high distance for a code form members. As closing, I also asked the ChatGPT what is his opinion. It's very funny, actually. It's very useful, and I recommend to everybody to use it, not blindly believe what it says, because sometimes it says crazy things, but it's not. It knows everything, every possible books which have ever been published in the world. So it's amazing. What your ChatGPT says that he recommends to use 6 to 10 times the RZ, which is again the smallest radius of inertia. It has recognized that the American standard gives a bigger limit, but it still believes that that is too high and something smaller should be used. So the ChatGPT says 6 to 10, Eurocode says 15, the American standard gives 40. What is the good value? It's basically up to the feeling of the engineer. What you can also do is that you can do some experiments in Consteel. Here I made a small comparison. Here on the right side, this model is the new approach where we have the unified model with one single reference line. And then I made here 3 alternatives by having different type of connectors, different connector spacing, and different releases along the element. And just based on that, I made some calculations, and I could see this just under the same loading. The only thing was the difference of connectors. When I used the new unified section approach, then I got a 90% working ratio, and the one with the biggest distance and not continuous but with some sort of degrees of freedoms are released, then I got up to 114%. So obviously it has an effect. There is a possibility for the engineer using Consteel to try to compare what the different assumptions can be. But if it is possible, then it is always recommended to try to use such a close distance and such a rigid solution as much as possible, and then fulfill the requirements to use this very much simplified approach using the new functionality, use just one reference line, and the unified section. Now I make a small example just to show how it works this in reality. It will be just a simple supported member, and I will just show the steps, which are exactly the same as if it was an IPA or a welded section. The only difference is that the creation of the double profile is a 2-step profile. I'm using now the new user interface of the new Consteel 18. I go on the create new empty model. It starts the same way as started in the past. I have an empty blank screen. I will want to define a 4-meter long simple supported member exposed to uniform bending moment or uniform compression. Also just to see how the different, these 2 main type of internal force have effect on the design results and effective cross sections and such. So in order to define my beam, first of all, I need to create the profile, the cross section. I could use a macro section filling with information, or I could use the library. At the moment, I decided to use a MedSec profile, which is not included at the moment in our officially provided libraries, but I already created this profile in my own personal library. I have here some profiles already pre-stored for certain use, and this folder called MedSec contains a 202 millimeter deep profile with a 2 millimeter thickness. As you can see, it's a parametric profile, so all the parameters are recognizable here, which were used to create the profile, but I don't need to remember the values and create them each time. I can use it as from my own library. So even if Consteel doesn't have a built-in library for the MedSec profiles, it's enough to just create them once, save them to the library, and then it can be used by anybody. At the moment, we cannot share the user library between different users, but the user library is a file which is saved to the computer. This file can be easily copied to another computer, and therefore immediately the user library saved by user A become available also for the user B. So now I just load this profile, and when I close the section, this profile appears in the section of the project, and I can go to the next step to define a double section out of it. So I select the double C icon, I select this single MedSec section which I had. I can specify a spacing if I want. Let's say I accept this default 10 millimeter, and I click on create. Now when I click on create, I have also the double section created, and if I want to see its properties, I can click on the properties button, and I see exactly the same type of picture which I have shown as a screenshot at the beginning, also with this blue infill color, and also all the section properties are visible here. What is important that this, for the double profile, we only have this sort of section modeling. If you remember, those who don't know Consteel, they probably don't know. In Consteel, there are two types of section models. One is used for structural analysis only. This is the one where we use the triangulation and we calculate all the section properties at the highest possible precision. And we have another simplified model, which is only used for the structural design based on the Eurocode, which allows the calculation of effective cross-sections and such. As we do only the analysis on the double cross-section, that simplified model, which is for the structural design, is not available for the double section because we will perform the structural design on the individual members. Okay, so this double section has only this triangulated and meshed cross-section model, but it provides all the necessary information for structural analysis. So now I can define my member using the usual functionality in Consteel. I need to select the double section, which will be the section of my beam, start point and end point. I just define now a 4 meter long member. You can see nicely that it really has the shape as I wanted. We can even recognize the gap between the profiles, so everything is in its full reality. I can define boundary conditions, fork support, as I would do for a usual section as well on the two ends. And I will now, as I said, define two load cases, one with the uniform load and one with the eccentric load, axial concentric loading. I switch off the dead load because it's not required. I change the default load case name to distributed, then I create a new one, which will be called axial. And now I define loads. For the distributed, I will want to define, let's say, a 4 kilonewton meter linear load acting eccentrically on the top middle position of the profile. It's important that in Consteel, every eccentricity has its own important role. It's not only a graphical visualization, it's really something which is taken into account during the calculation. And when I place the load, it's visibly flying in the air. If I activate the profile, then I can see that it's not just arbitrarily flying in the air, but it's exactly at the top of the boundary box. So now the boundary box is clearly valid not for the single section only, but for the double section all around. And now when I set the axial load, I will this time create a negative 50 kilonewton placed and the support with the roller. I create two load combinations. Of course, I could use the built-in wizard, but at the moment, this is just a test. So I do two simple load combinations. And when I come to structural analysis, I will perform just the first order analysis, but because I want also buckling calculations, lateral torsional or flexural buckling of my members, I activate the buckling analysis as well, and then I run the calculations. When I go to the first order results, then I will see that under the uniform loading, we have a bending as we expect. And if we have for the axial load, then we see that there's a shortening of the member as we can expect. If we look to the internal force diagrams, then what we see is that just one reference line, we have results on the reference line, but anywhere we are running along the length, we see that Consteel is already preparing the internal forces for structural design. So the single internal forces on the singular reference lines are already prepared, splitted into left and right. So here we say left, half of the axial load, and right, half of the axial load. And if we come to the global checks for structural design, I also activate the buckling check. Then what I will see is that we see the two profiles separately, each have colors, because now the loading is symmetric. All the loads on the left and the right member are the same, but anyway, we are running with the mouse. We see that we have two results. At the moment, they are exactly the same. Anywhere along the member, clicking the right button, I can select whether I want to go the design of the left or the right member. And as I said at the beginning, the design will already call the usual single profile. So this is not the single profile, double profile anymore, but the single profile. The internal forces have been prepared by Consteel consistently on the single element, and on the single element we can perform all the structural design verification as required. For the bending condition, we see that we have compression on the top flange, and there it was required to apply a thickness reduction due to distortional buckling. And if I go to the other load case with the axial compression, we can see, as we expect, that the web is in compression. Therefore, there will be also an ineffective part of the web. Plus, similarly, but not only on the top, but also on the bottom flange, we have thickness reduction due to distortional buckling. But the section doesn't work, at least for the bending condition, we have more than 100%. For the pure compression, we are below 100%. Against lateral torsional buckling, one typical and easily applicable solution is that if by any reason there is anything like a roof sheeting or something connected this member in reality, we just haven't modeled yet, then we can take this into account. Let's assume that this is a rafter and we have a trapezoid decking in the real structure positioned and fixed to this element. In order to take this into account, we will select from the Consteel library a profile, let's say a Hirsch, positive positioned, just with a small corrugation. We can decide whether we want fixing at every rib or only at every second rib. What is the length of the shear field, where we take into account the membrane stiffness of the trapezoid decking. And we can also say that on this member, let's assume that in reality there are at every 2 meters such a beam, and just 2 meters is the tributary width where the stabilization is applicable. And again, in Consteel, every eccentricity counts. Therefore, we need to also specify that at which level this trapezoid decking is connected to the member. This is on the top member, top flange level. And when I click on the element, then there will be also graphically shown that now the trapezoid decking is attached to the top flange. And I just need to repeat my calculation again. What we will see now that looking to the buckling results, the first buckling mode, which is a lateral torsional buckling mode shape, the two elements are clearly moving together. You may have the feeling that they are moving separately because sometimes you see a gap, but this gap is just simply a consequence of the original gap between the two profiles. The two profiles are moving together, but now the critical load multiplier is above 1, so that means that we have a chance that it will work also for the lateral torsional buckling check. And when I click on the verification, I can see that now the 200% got drastically reduced down to 75%. So the structure works. Of course, regarding the compression problem, it didn't change too much. The sheeting, which is very efficient to be applied on the compressed flange against lateral torsional buckling, doesn't play too much role for a flexural buckling. And just as a certain conclusion, I want to say something even more complicated is that, as I said, it's not just for simply floor beams or columns or such can be made from I sections, but as complex things also as a complex porta frame. Here, for example, without any spacing, two sections are used for the column and also for the rafter. And usually for these type of structures, what is very critical is the knee region. In a porta frame, typically this is a region which is exposed to bending moments. The typical porta frame has pinned base or fixed base. Here in this case I have fixed base, but it's always somehow assumed that the column and the rafter are connected with the moment bearing connection. This gives the typical behavior what we expect from a portal frame. But to connect such profiles with moment bearing connections is very complicated. It's not impossible. The connection design is very tricky. You can use special softwares to make the connection design, or you can find probably more easy to be understood structural configuration, such as typically a solution when the bending moment is not directly created, bending moment transfer is not directly created between the column and the beam member, but an additional diagonal element is used, and the connection between the column and the member can be even a pinned connection. And typically when this pinned connection is used, then only a single section is used as an extension of the double section column and the double section beam. In one situation, the left side is extended, on the right, the other, and then they are just simply nicely connected like this. Here I was able to define this part of the element with the new double section, and here this part I used a single section and I specified an eccentricity to be exactly the same line as the left or the right side of the member. And what is important that in Consteel, this is again is not just something which looks nice on the picture, but if I run the calculation and I see all the results, we can see that the elements are nicely, this is now a buckling shape which is required for the stability calculation. What you can see is that the elements are perfectly nicely continuing without any break, without any gap, without any discontinuity between the single and double member. This is a proof that mechanically everything is perfectly and consistently transferred. And when we come to structural design, the whole thing becomes as simple as with the simple supported member. I just activate the buckling check and run the calculation. And if my results are below 100%, then I can be sure that the structure works correctly. This was my presentation. As I understand, there are some questions which I was not looking to. I don't even know how to find them, but where are the questions? Beamcad and the webprop. I think all have been answered, no? Can we obtain bonding forces for connectors on double sections? No. When you use this sort of new uniformed solution, then basically we assume that the bonding forces are invisible. If you want to see what these connector forces are, then you must stick to the traditional approach and define link elements, and from the link elements you can retrieve the connector forces. How the shear and rotation restraints work with the double profiles? Yeah, like with the single profile. We don't believe in machine, we believe in what we see. Good. I think you can see everything nicely in Consteel, and if you see deformations which are close to what you expect, then hopefully you can trust a bit more the machine. Stresses from torsion and double profiles. Yes, from torsion we can have all the stresses. As I said, for structural design we use the single profile model, but all the internal forces are mechanically correctly together completed with even by moments are transferred to the single member. So you can see separately, but you can see correctly the stresses on the left and the right side of the profile, assuming that they are moving together. Steelspace is, it's nothing to do with that. Where are arrow checking applicant? Okay, yes, model diagnostic. For the shear field stiffener, but there was a limitation of the function regarding the orientation of the profile, could it in small inertial direction. To be honest, yes, because we always assume that the shear field will be used against lateral torsional buckling. And lateral torsional buckling is something which is always around the smallest inertia. So therefore, it's still the case in Consteel, we cannot rotate the shear field. Theoretically, it could be possible to do. And I think with some tricks, maybe you can even achieve it, but normally we always assume that the shear field is the tool against lateral torsional buckling. Therefore, it works against, it helps to stabilize the smaller inertia of the section. Can you show connector forces from the ligaments in the traditional approach? I don't know where is, I had something here in the model. I don't know what type of forces are in, because of course, depending on the type of force we can define. If we use a link element, then in the link element itself we cannot retrieve internal forces. But if you use as a connector a real virtual beam of any sort of rigid enough profile, and use it as a start and end point between the two, then this will be recognized by Consteel as an arbitrary beam. And on that arbitrary beam, we are showing all the internal forces as usual. So if you use a link element, then unfortunately we are hiding the internal forces. This is already something which has already been asked several times why we do, and to be honest, I don't know. I think we need to reconsider this and maybe to show the forces. There was a clear definition that the beam has internal forces and the link element is not a beam. Even if it looks like to be a beam, it's not a beam, it's a link element. But of course, the question often comes what forces it transmits, because definitely it transmits forces. And then if somebody wants to design a connector for this force, then it's quite a logical question what the forces are. At the moment, the link element is hiding the internal forces, but you can easily replace the link element at any given desired location into a beam element, maybe using a pipe section, high enough cross section, or what I typically do is I define a virtual profile, a new profile, and with the new profile, a steel material, I create a 1,000 times bigger Young modulus to become very rigid. And then I define this beam with the right boundary conditions at the desired location. And when I run the analysis and I can look to the connectors, if I use the special profiles, I can easily select with the nice auto portion functionality only these link elements, and then I can see the internal forces on them, because in that model they are acting as normal beam elements, and then all the internal forces are visible. This is maybe a bit painful, but at least it's possible. Please show if they're very useful. I don't understand why you are hiding them. I also don't understand. Maybe this will be the new function of Consteel 19. If you have no other question, then thank you very much. And I hope you will enjoy this new, the best ever Consteel once we release soon. Thank you very much and have a good day.